All right, welcome back. We're going to talk a little bit about a few more properties of water that make it unique because of its polar nature. One, oftentimes when you go and you take a look at a pond or a stream, you'll notice that there's a little insect that walks on the surface. This is a bug called a water strider or a pond skater. They have these special unwettable hairs that allow them to skate or move around the surface of a pond. They're scavengers. You might notice that insects or things like that will often get stuck in what we call the surface tension of the river or pond, and these will skate over to it and poke them with their beak and then suck them dry. They communicate by means of making waves. We've actually calculated or observed males doing territorial displays where they can produce 90 waves a second. Imagine sitting in a waterbed and moving that up and down at 90 waves a second. That's pretty remarkable. But surface tension is caused by the strong cohesive nature of water. Remember, water likes to stick to itself. And because of that strong cohesion, we almost get this beautiful little thin film of water at the water-air interface. In fact, if the surface of the substance that the water is on is nonpolar, for example, let's say you have a freshly waxed car, you might notice that the water is so cohesive that it goes and forms a drop, almost a sphere or a hemisphere. Pretty cool. But surface tension is created by this highly cohesive nature of water because it's forming hydrogen bonds. Water also has what we describe as a high specific heat. Specific heat is a physical measurement. It's the amount of heat required to raise the temperature of a substance. A great example of measuring specific heat is when you go and put a pot of water on to boil. So you have this nice metal pot. You go and you put it on the burner of the stove, turn on the burner. If you come back a couple minutes later, if you try to touch the metal pot, you would probably burn your fingers, right? But if you stuck your finger in the water, you might notice that the water is still cool or still tepid, right? That explains a difference or demonstrates a difference between the specific heat of two substances. The metal has a much lower specific heat. It doesn't take a lot of energy to change the metal, the temperature of the metal. The water, on the other hand, takes a long time to heat up. And that's because water has a high specific heat. In fact, here's a comparison. We use water as our standard for specific heat. And so water is defined as having a specific heat of 1. Anything less than 1 is something that requires less energy to heat up. And for example, if you start looking at certain types of metals, for example, gold and silver and copper and aluminum, that's the reason why they heat up so quickly. It's because they have a low specific heat. Right? The reason water has a high specific heat is, as we mentioned before, it takes a lot of energy for a single water molecule to sort of break free from those other water molecules. They're being held together. They're so cohesive. Every water molecule is being held by 4 other water molecules. And to get those water molecules moving, and that's what temperature is, it's the kinetic energy of a substance, to get it to moving has to resist and overcome that strong cohesion. And so water, because it has a high specific heat, takes a long time to heat up. Oftentimes we describe water, especially when we're trying to boil water, we say a watch pot never boils because it takes a long time for it to heat up. Now, water isn't the thing with the highest specific heat. As you can see over here, you can see ammonia has a fairly high specific heat, 1.23. So it's even more cohesive than water is. Now, oftentimes when you go and you look at blacksmiths, when they go and take a piece of iron or a piece of steel or a horseshoe that's red hot, and they quench that in a bucket of water or a barrel of water, you might wonder, you might think, wow, I bet that temperature of that water really, really heats up. It doesn't. Water has such a high specific heat that if we went and measured the temperature of the water prior to quenching a horseshoe to after quenching the horseshoe, you would find that the temperature change would be very, very slight. We actually tried this in lab a few years ago. We took some big nails and we heated them up with a Bunsen burner, and then we stuck them in a glass of water and then tried to measure the temperature change, and we found no temperature change. The specific heat was so high that it resisted that, super hot metal. This turns out to be really, really important. If you're an organism that is living in an aquatic system, let's say they're swimming around in a pond or a lake or a river or an ocean, you don't have to deal with a lot of temperature fluctuations. All right? For example, if we went out to the ponds here on campus on the golf course and measured the high and low temperature of the pond over a 24-hour period, you might see that it might fluctuate maybe less than 5 degrees. However, if we went and measured the air temperature over a 24-hour period, you might see that that fluctuate might 20 or 30 degrees. Water, because it has a high specific heat, makes an excellent environment, especially for organisms for dealing with temperature fluctuations. One of the benefits of having a body that is mostly water is that it helps us maintain a constant internal temperature. For example, when we go and during the summer, sometimes you'll hear about heat waves. You'll hear about heat waves that strike big cities, usually in the north. For example, we might have a heat wave in Chicago, heat wave in New York City, heat wave in Paris, heat wave in London. And oftentimes with heat waves, we'll have accompanying deaths. Who is more likely to die in a heat wave? If you watch the news or read the paper, you find out that oftentimes it's elderly people. All right? Old people, as they get older, lose water. As a male, we might have 55% water, all right, as an adult male. But once we get up to our 70s or 80s, where water concentration might be down to 40%. Now, with less water, you become more susceptible to temperature fluctuations. So when we have weather extremes, those people who have less water are going to be more susceptible to things like heat stroke and heat exhaustion. So water has this remarkable ability to help prevent big temperature fluctuations. Since I'm an entomologist, I'm always fascinated by insects, and this is one of my favorites. This is a very common insect that we have here in South Alabama. This is called a spittlebug. On your bottom left is what the adult looks like, but if you've ever walked around a meadow and you kept see these, almost looks like somebody just went and spit onto a plant. And you go, who would do that? Why would somebody come way out here and hork a loogie onto this plant? Well, you're not looking at human spit. You're looking at a nymph. This is a baby spittlebug, and it does a very interesting thing. It feeds on plant juices, and it protects itself by covering itself in this wet foam. Now, I thought, well, that's kind of a cool little predator deterrence, but it really plays an important role in preventing big temperature fluctuations. Because it's so wet, that little pond that that animal has made actually goes and prevents it from having big temperature fluctuations. You're seeing a way for this animal to help maintain a fairly consistent internal body temperature. Another important idea that we have in physics when it comes to water is the idea of evaporation. All right? We often describe gases as vapors. All right? Substances come in basically three basic stages. We have solid, liquid, and gases. All right. We also have plasma, but we're not going to talk about plasma in biology. So when something goes from a liquid state to a gaseous state, we say that it has vaporized. Right? And when we talk about evaporation with water, as I mentioned before, that's when an individual water molecule has broken free from its four neighbors, and has become an individual water molecule, has turned into a gas. And we call that process evaporation. Now, turns out that for different substances, there are different temperatures that are required for something to convert into a gas, something to break those bonds and become an individual free molecule. And that temperature that's required to do that is what we call the heat of vaporization. The heat of vaporization. Now, just like specific heat, water has a very high heat of vaporization. It takes a lot of energy for water to convert or transform from a liquid to a gas. Turns out that because of this process, we can use the evaporation of water as a way to cool ourselves off. In fact, we describe it as evaporative cooling. On our bodies, as humans, we have over 3 million sweat glands. Right? They empty into pores on our skin, and we're constantly going and secreting this thin layer of water on their surface. And when it's hot, and when we're exercising, all right, we secrete even more. On a really hot day, when you're really exercising vigorously, you can lose up to 12 liters of water. So these little glands are constantly secreting sweat, and sweat is 99% water. Right? Now, the reason that we put this layer of water on us is that water can absorb a tremendous amount of body heat. So that water absorbs all that heat from the interior, and that heat is released as that water evaporates, as we go from a liquid phase to a gas phase. That's why we do this evaporative cooling. It can really, really cool us off. Now, we're especially well adapted for it. We're fairly hairless apes. All right. If you think about where we originated in near the equator in East Africa. All right. One of the things that we got was a huge amount of sweat glands. Right? So we are very well adapted for living in places that are fairly toasty. Right? Other animals, for example, if we look at dogs, they have a few sweat glands on their pads and around their genitalia, but their main form of evaporative cooling is going to take place through their tongue. So when you watch a dog pant, that's what's going on. That water that's coating the tongue and the inner of the mouth is actually absorbing a huge amount of heat and then evaporating and reducing the temperature. Now, my little vulture that you see here does a very interesting way of evaporative cooling. They don't have sweat glands, but they do have water in their feces. And you'll notice that when you look at most birds, they don't have any feathers. It's just scales on their feet and their legs. And so vultures do a very odd thing, right? In fact, when we look at feces, we find that a lot of it's water. So they poop or defecate on their feet, and the water evaporates off and cools them out. Kind of a gross way to do it, but it's using the same principle. So, let me explain how this evaporative cooling works. Let's imagine, if you will, that we're going to go and take everyone at LBW and we're going to race them. So everybody has to line up and we're going to do a 100-meter dash. So everyone goes and runs 100 meters and we time them. Right? If we go and we take all those results and calculate an average, we'll find an average speed for LBW, the LBW population. Now, let's say that we take the top 10% of the runners, the ones with the fastest times. Right? So that's 10% of the runners. And we transfer them down to, let's say, Enterprise Community College. Right? What happened after we transfer them? What happens to the average speed of LBW? It drops, right? Well, that's exactly the same thing with evaporative cooling. If we think about a container of water, you have water molecules moving around in there. There are some that are fast, there are some that are medium, there are some that are slow. And we actually go and measure that temperature as the average kinetic energy. Now what happens is when we have evaporation, right, the ones that are moving the fastest are the ones that evaporate and leave. It's like our fastest runners transferring to Enterprise. What happens to the average kinetic energy of the remaining water? It drops. That's what creates the cooling. That's what creates the cooling. And we say that water has a high heat of vaporization. It takes a lot of energy for water to transform from a liquid into a gas. The last thing I want to talk about is a very strange thing. This is probably one of the most bizarre things that water does. And that's when water becomes a solid. Now, most things, for example, let's say that we had a glass of liquid benzene. Right? And we took some liquid benzene and we went and we froze it solid. So we have an ice cube of just frozen solid benzene. And we put it in a glass of liquid benzene. What would that solid cube do? Would it float or would it sink? It would sink. It would sink right to the bottom. And if we do that with most substances, we find they do exactly the same thing. Substances, when they are a solid, are more dense than liquid. So in a solid phase, those molecules and atoms are closer together. That makes them more dense. When they're a liquid, those molecules are going to be farther away from each other, which makes them less dense. So for most substances, we're going to find that they are going to be more dense as a solid and less dense as a liquid. Now, water is extremely weird because it's the reverse. For example, if you freeze water and make it into an ice cube and put it in a glass of water, it is not going to sink. It is going to float. That ice cube is less dense as a solid, which is completely backwards. Those water molecules are actually farther apart than they would be in liquid. In our little PowerPoint slide here, if you look at the bottom right, is what water looks like as a solid. You can form it forms a lattice. And the picture on the left is what water looks like as a liquid. You can see in the liquid, those water molecules are physically closer together, which makes it more dense. Right? Density is, mass divided by volume. So it's, as you can see, you have more of a substance in a smaller area. Right? The molecules are closer together. And if you look over there, you can see, wow, they're much farther. That's what makes it float. Now, that's pretty remarkable. The other thing, too, about water is not only is it less dense, but because the molecule gets farther apart when it becomes a solid compared to when it's a liquid, that means that that water expands as it transforms into a solid. In fact, we describe ice, we describe, the formation of ice as the expansion of water. In fact, water can expand by 10% of its volume. We've all had that experience where we've, put a water bottle in the freezer. And we come back and the water bottle has exploded because the ice has expanded and busted the water bottle. The amazing thing is how much force there is. We find that as water expands, it generates a force of 36,000 pounds per square inch. That's huge. 36,000 pounds per square inch. That is powerful. In fact, we find that that is a powerful form of erosion in geology. I have a picture of a pothole here. When you go up to a northern state, you'll find a lot more potholes in places like Michigan and Iowa and Colorado than you would here in southern Alabama. The reason for that is because up there you have a lot more freezing that goes on. Now, how a pothole forms is that as water seeps into tiny little cracks in the pavement, when it freezes at night, that water expands by 10% of its volume. And remember, 36,000 pounds per square inch. So it makes a little bigger crack. This cycle keeps repeating itself over weeks and months. And over time, eventually, we get a big pothole. Right? That expansion, right? Then turning liquid, expansion, turning liquid, expansion, turning liquid, becomes extremely powerful. Now, if water is less dense as a solid, that means that if we look at a frozen lake or a frozen pond, that means the water underneath the ice is going to be warmer than the frozen layer of ice on the top. Isn't that weird to think? That when you look through the ice and you see fish swimming around, they're swimming in water that is above freezing. Turns out that we know the temperature at which water is the most dense as a liquid. It turns out that at 4 degrees Celsius, that's 39 degrees Fahrenheit, 4 degrees Celsius, 39 degrees Fahrenheit is when water is the most dense as a liquid. So, let's say we go to a pond on a chilly, chilly frozen day, the surface is frozen. If you went and put a thermometer and measured the temperature at the bottom of the lake or the bottom of the pond, you would find that it would be 39 degrees. The denser water is going to be the lowest, all right, and less dense on top. So you get this stratification, and you can see here, for example, in the bottom left where the box is around, you can see, look at the temperatures there. All right. Here at the bottom, you have 39 degrees. As you get closer to the ice, it gets colder to 32. That's pretty remarkable. Now, imagine what the world would look like if water acted like any other substance when it became a solid. If water did not become less dense as a solid, let's say it became more dense as a solid, our world would look completely different. What would happen is all the oceans would freeze, freeze from the bottom up. All the lakes would freeze from the bottom up. All the ponds would freeze from the bottom up. And what would happen is in the summertime, in the oceans, we would just have a couple of 100 feet of water that was liquid. Everything down below that would be frozen solid. Right? That would really limit the amount of area for living organisms. That's pretty remarkable. So all those deep sea organisms, they wouldn't exist. They'd all be blocked by ice. So, water is a weird, weird molecule, but we're really lucky to have it because our bodies and our world, all right, is adapted because of the strange nature of water.